So now that the exam is over, and we're done with the material for the 4th exam, we can now start working on the material for the last exam, which is the 5th exam. So, one thing to tell you is that whatever we do on this exam will not be part of the final. Reason for that is basically we're going to take the exam on Wednesday, and then your final is going to be like a couple days later. So there's really no point in testing you over the same thing basically within a couple days or a week. So whatever we do here, it won't be on the actually final exam. So it'll only show up here on the on this 5th exam. So the first part we need to talk about then for this upcoming material is fluids. So we're going to start looking at fluids. So the first to understand what a fluid is, we need to first talk about states of matter. So in general, there are 4 different states of matter. So there's 1, 2, 3, and 4. So the first state is what we call a solid. So we define a solid then as a substance which holds both its volume and its shape as it is being moved around. So for example, if I grab my cell phone here, my cell phone then is a solid because as I move it from one location to another location, no matter what I do to it, the shape of it and the volume of it stays exactly the same. So here for a solid, this is something which, there goes my cell phone, remains its shape and volume. Okay. Now, the reason for this is because a solid is made up of a lattice. So in this case, here would be the lattice structure of my solid. So basically here, this thing then has very strong nearest neighbor attractions. These nearest neighbor attractions hold this thing together. Since this thing is held together, imagine that these things are basically springs. These atoms actually are vibrating, and as they are actually vibrating, they are stuck basically in a rigid shape. So as I move this thing around, even though this thing might twist and bend a little bit, the lattice basically keeps it together as a whole. So in this case, it has to maintain both its shape and its volume due to this highly attractive nearest neighbor attractions between all of the atoms. The second one is what we call a liquid. So a liquid is a material that maintains its volume but not its shape. So in this case, it maintains volume but not shape. So I know that because if I took basically water from this particular water bottle here, and then I opened it up and I poured it into, say, my gigantic coffee cup here, as I pour it then into my coffee cup, what would happen then is I maintain the amount of volume which is inside of here, so the amount of water I have inside of here, which is 16.9 fluid ounces, would still be 6.9 fluid ounces within inside of this coffee cup, but it would take a completely different shape, where that shape then would be determined by the shape of the container. So here it has this particular shape due to the fact that it's in this container. But when I pour it into here, it would now have a different shape, which now corresponds to this container here. But I know if I pour it from one into the other, it must maintain its overall volume. Okay? Now, reason for this is because once I go from a solid to a liquid, what happens then is I have to break these nearest neighbor attractions, which basically means that I break this lattice structure so that the liquid now has no lattice structure to it. However, it still has fairly large nearest neighbor attractions, which basically means that if I was looking inside of the fluid, what happens in this case then is all of these molecules are going to be bunched up together very closely due to the fact that there's still a large nearest neighbor attraction, but I can still move these guys around. Right, so basically this center atom is going to be pulled in this direction, pulled in this direction, pulled in this direction, pulled in this direction. But on average then, if I sum over all of these, the total force then is going to be equal to 0, right? Because all of these are exactly the same molecules, just pulling in different ways. Now, one interesting thing about liquids is liquids typically have what's called a surface tension, where that surface tension is because if I was looking at basically the top layer of the liquid, in this case if I was looking at that center atom, so here's my center atom, I'll have another atom here and I'll have another atom here, but these two top ones that are supposed to be here are now gone due to the fact that I'm cutting off the fluid here, which basically means that this thing is going to be pulled in general in this direction and in this direction, which means the net force on this guy will end up being downward, right? So it's going to be the direction of the net force. So what that does then is all of the atoms which are basically near the surface end up being pulled downward, and as they're being pulled downward, they also end up being pulled inward, which basically means that you create basically a membrane on top of here. This membrane is what we call the surface tension. This is described by what's called gamma, which is the surface tension. That's about as much as we're going to talk about it here. We're not going to go through the math of all of that, but just note that typically what happens for most liquids is they do have this surface tension, and again, it's because of the unequal number of atoms which are surrounding it, which ends up causing this force. Now, surface tension, this is typically what hurts when you jump into the water. So for example, if you were jumping from a high dive board into the water and you screw up and you end up doing a belly flop, what happens is that this is what causes the pain, right? This is basically what acts as kind of like a membrane or like a surface, which then sometimes can basically be like hitting concrete, right? So it's almost as hard as, say, a solid when you're actually jumping to it. So if you ever watch a high diver actually jump into the water, what you'll notice is either there's going to be two people at the bottom of where he's going to land, say at the bottom of the ladder, they have their feet in the water and are actually kicking the water, or there's going to be a wave machine where that wave machine will actually cause the water to be choppy. And the reason for that is what you're trying to do is by making the water choppy, you're trying to break this surface tension to get rid of all of this nearest neighbor attraction on here, so that way it doesn't have time to settle and doesn't have time to actually create then a surface tension. So this is what we call a liquid. So again, a liquid maintains its volume but not its shape. Next one we have is called a gas. So a gas is something which does not maintain its shape nor its volume. So this does not maintain shape nor volume. So in this case, for example, you go over here. So let's say this now empty water bottle, one of my wife's water bottles. Let's say I had some sort of gas inside of here. So I don't know, let's say it's nitrogen or oxygen or helium or something like that. And I dump it inside of this container. But now if I open the container, what's going to happen then is that all of that, say, helium is going to come out. That helium then is going to expand as far as possible, which means it's going to fill up this entire room. Now, as it does that, then the distance between the helium atoms will actually end up becoming much bigger. So in that case, there's not going to be very strong nearest neighbor attractions. And this thing is going to actually change its shape by filling up the entire room. So initially, its shape and its volume was that confined to inside of the water bottle here, but as soon as I open it up, its shape now becomes the size of the room, and its volume now becomes the amount of volume, which is that of the room. So a gas then is something which has nearest neighbor attractions, but these things are ridiculously small. Now, there are different types of gases. The one that we're going to be dealing with primarily are what are called ideal gases. An ideal gas is a type of gas which basically the nearest neighbor attraction is only that of gravitational, which basically means that if I had an atom here and say another atom here, this guy is going to be attracted to him, he's going to be attracted to him, but again, only gravitational. So here the nearest neighbor's attractions are ridiculously small. So there is almost no nearest neighbor attractions, which is why these things are going to span out as basically as much as possible because they have no real nearest neighbor attractions. The last state of matter is what's called a plasma. So a plasma is effectively a gas, but it's an ionized gas. So this is an ionized gas. So what does that mean? So that basically means that all of these molecules which are then inside of the gas are either going to be positively charged or negatively charged, which means that overall, what I'm going to have then are free charges out flying around in space. Now, what does that mean? So an ionized gas is, let's say initially I had what? Oxygen. So in that case, what you end up doing is you strip off an electron due to the fact that the temperature is so high, or the energy is so high, and in that case, the oxygen becomes charged, in this case positively charged, while the electron then flies off that has a negative charge. So basically in my space, within my gas, I have positive charges and negative charges. Now, if it becomes ridiculously high, right, the temperature becomes very high, or the energy becomes very high, what will happen in that case then is that things like hydrogen won't be a hydrogen atom anymore. What will happen then is that the proton and the electron will completely strip away from each other. So I won't have hydrogen anymore. I'll just have protons and electrons, which are basically flying around in my space. So this is what we call plasma. So particular examples of plasma is the ionosphere. So the higher upper portion of our atmosphere. When the sun shines then onto our upper atmosphere, what happens in that case then is what? It ionizes because there's so much energy carried by the photons from the sun that it actually kicks off the electrons within the upper atmosphere, which then ionizes the gas, so we actually have a plasma. This is actually what, if any of you are familiar with the UNITE project, so the CubeSat project that USI has been part of, this is what they're actually trying to measure. So they're trying to measure properties of that ionosphere in that plasma. So they're actually mostly looking at more of an intermediate range as opposed to the very upper portion of it. Another place that this is actually important are places like stars. In the center of a star, it's going to be a plasma. Early universe is also going to be a plasma as well. So in the early universe, shortly after the Big Bang, the universe was so hot that when you actually had particles which were created, so again, protons and electrons, it was so hot that it was more energetically favorable for these guys to be flying around as opposed to combine to each other to create hydrogen. So basically what that means then is that what? In the early universe, as light was given off, the light didn't actually travel very far because it turns out that light is actually bound to, or at least attracted to, positive and negative charges, which basically means that what? My photon would be sucked up by, say, the proton here, and then eventually be emitted, but then it would go only a short distance before it would be sucked up by the electron, and then be emitted again, and then sucked up by another proton or an electron, or etc. This is what we call the mean-free path. We'll talk about this eventually, but basically what happens then is on average, the photon is only traveling a very short distance, which made that the early universe was actually opaque. But as the universe actually expanded, it cooled down as well, and as it cooled down, it became more energetically favorable for the protons and the electrons to bind together to create hydrogen. Once that happened, this thing now, when these two are combined together, this becomes electrically neutral, which means that the photon is no longer actually attracted to it. It'll actually free stream, and then it's been traveling to us since that time to now. This is what we call the cosmic microwave background. So the CMB is actually what we see left over from the time of what's called recombination, which is when the proton and the electron end up binding with each other to then create hydrogen, and at which point the photons can now actually free stream to us, mostly unabated. And then what we can see then is that time when we actually look at the CMB. So experiments like Planck and all those different ones that are actually looking at the CMB are trying to understand what happened at that time. So, off topic, but that's fine. So in this case, again, these are our four states of matter. So we have a solid, we have a liquid, we have a gas, and we have a plasma. What we call a fluid then is actually these three together. So a liquid, a gas, and a plasma are all what we call fluids. So a fluid is either a liquid, a gas, or a plasma. So we just use the generic term of fluid to talk about any one of those. Now we do typically distinguish a liquid as opposed to a gas or a plasma, because again, the distinguishing feature here is that a liquid can maintain its volume where a gas and a plasma does not, because again, a plasma is just an ionized gas. So liquids then get a special name, and this is what we call an incompressible fluid. So incompressible just simply means that we cannot compress it, we cannot change the volume. The only thing we can change is its shape. So specifically, whenever we're going to talk about incompressible fluids, which we'll talk about those every once in a while, we mean a liquid, which is something that maintains its volume. If it's not an incompressible fluid, we'll just randomly call it a fluid, and then it's going to be any one of these different scenarios. So this is what we call a fluid. So again, a fluid is either a gas, a liquid, i.e. an incompressible fluid, or a plasma. So good. So something else we need to talk about, and we're going to use that term a lot, is what's called density. So let's talk about density. So what is density? So density, in this case we mean specifically mass density, is defined as the total mass divided by the total volume. So this is then equal to the mass per unit volume. So this then has units of kilograms per meter cubed. So this is what we call density. So density, so typically when we talk about density, we're really only talking about solids, that first state of matter. And the reason for that is because, again, and liquids. We can talk about density with liquids as well, i.e. incompressible fluids. But we can't really talk about a density of a gas because, again, if I had the gas in the water bottle and I open it up and it spread out to this room, what happened was the mass stayed the same, but the volume now has drastically increased. And since the volume has increased, that means the density has gone down. So to talk about the density of a fluid, it has to specifically be in some sort of container for us to actually be able to talk about it. So typically when we talk about density, we're really only talking about that of a solid or liquid, unless it's a gas which is in some sort of, again, container. So we will hear a lot, you can talk about the density of air, and the reason for that is typically, in this case, we're talking about the air that we breathe, which in this case is confined to the atmosphere. So in this case, on average, or like roughly speaking, the atmosphere has a spherical shape to it, which means that there is some sort of height that this thing has. So if we know the total mass, and we also know the height, we can then talk about the density of the air, which we'll use a lot. So typically in this class, density of air is going to be about 1.29 kilograms per meter cubed. So again, this just means the density of the air within the atmosphere that we breathe. Another thing we're talking about is pressure. So let's talk about pressure. So pressure then, we're going to call that little p. So pressure is defined as, so typically when we talk about pressure, we're going to talk about, let's say we have some sort of surface area here. So this is our surface, which isn't necessarily flat. That's why I'm kind of drawing it this way. And let's say I have a force pushing down in this particular direction. Okay. So this is the limit as delta A goes to 0 of the perpendicular of the force divided by the change in area. Okay. So what does this mean? So this means that if I had some sort of, again, say if I was looking at the surface of the Earth and I had some sort of surface which was not flat, then basically what we do is we're going to draw a area, let's call that guy delta A, and then I'm going to take that area, say that's here on the surface of the Earth, and I'm going to shrink that down small enough so that this area then becomes approximately equal to a flat surface. So the force then is the force per unit perpendicular area, so in this case only the perpendicular portion of the force, in a section where the area is then a flat surface. So in this case, this then is going to be equal to the derivative of the perpendicular portion of the force with respect to the area. Now, if I had a force then, which was only perpendicular to a flat surface, so in this case, if this was my flat surface with a area A, and I was applying then a force which is straight down onto this, so it was perpendicular to this area, the pressure then is going to be that perpendicular force per unit area. So this thing then has units of, so remember force has units of newtons, Area has units of meters squared, so this thing has units of what we call a Pascal. So Pascal then is the SI version of the units of pressure. So of course there's all kinds of different units of pressure. These things are all related to each other. So for example, 1 atmosphere, where an atmosphere is equal to the pressure that you would feel at the surface of the Earth at sea level under standard conditions, so standard temperature, standard humidity, standard etc., is equal to 101.3 kilopascals, which is equal to 760 what's known as torr. So this is the relationship between each one of these. So what is an atmosphere? So to kind of give you an idea what atmosphere is, so let's say again, here I am on the surface of the Earth. So here I am. And imagine then you draw a cylinder around yourself, which extends from the ground at sea level all the way up to the top of the atmosphere. And then what an ATM then is, it's the pressure, which is the force per unit area that you feel from all of this air inside of this column crushing you down all the time. Okay? This is what we call an atmosphere or atmospheric pressure. So again, if I look at myself and I have a cylinder which goes around me all the way up to the top of the atmosphere, extending from the ground at sea level, then this is the amount of force per unit area that is crushing me down at all times. So basically, meaning that what? If I go to a lower pressure, what ends up happening in that case then is my body will actually start to expand because I don't have that pressure pushing me in, keeping my body together. So if I go higher up, meaning where there's less pressure, what will happen is my body will actually start to expand because my body is actually has less pressure trying to hold it together. So this is actually what happens when you go up in an airplane. So when you go in an airplane, they actually try to pressurize the cabin, but you feel your ears popping and your ears actually kind of hurt. And the reason for that is actually your eardrums are starting to expand, and they're expanding too much around your skull, which basically is crushing them in, which is causing that pain. So this is what we call an atmosphere. Okay. Now, question for you. We're going to try something a little bit different today. So I want you to write the answer to this in the comments before we actually move on. So no cheating. Make sure you pause the video and then answer in the comments, and then we can go from there. So if I took a person and I put them in a bed of nails, so there's my bed of nails, and I laid down a person on top of my bed of nails. So there's my leg, there's my arms, right? So the question then is, why is this person not impaled? So why is it that a person can lay on a bed of nails and not actually impale themselves? So again, pause the video at this stage, write something in the comments and tell me why, and then we'll discuss the answer. All set? Good. The answer is pressure. So the reason for this is what? The force pushing down in this direction is simply the weight of the person. We can't change that. So if you think about the fact that if I took my foot and I stepped on a single nail, that nail is going to go directly into my foot because I have what? This force, which stays exactly the same, but now I have a very small cross-sectional area that I'm actually stepping on, i.e. just a nail, which means that the pressure then is something very large, which is actually going to impale myself. But if I lay the person down then over the bed of nails, in that case, then the cross-sectional area now becomes, if I was looking at the back of the person, right, so here's the back of my person, then it now becomes the effective cross-sectional area of the person, which means this is now a much, much larger cross-sectional area, which means that the pressure has now drastically decreased, which means the force per unit area on that person is now so small that they don't actually impale themselves. So this is how you can actually lay down on a bed of nails and not have any difficulties and not impale yourself, unless the distance between successive nails is actually too large, and in that case, you start running back into the same problem again, and you will start to actually impale yourself. But here, if you think, again, the density of the nails is pretty small, then you won't have any issues at all. So good. So these are quantities that we're going to see. So again, we're going to talk about density a lot. We're going to talk about pressure using fluids. So good. So the first topic we want to talk about is what are called static fluids. So we'll talk about static fluids. So what's a static fluid? A static fluid is a fluid which is at rest. Okay. So basically what that means is that the fluid is at rest relative to the container at which it's at. So this is at rest relative to the container. So what does that mean? So that means that if I had, say, fluid inside of this container, and I was moving this container, the fluid would still be at rest because the fluid inside of my container, i.e. my overly large coffee cup, is not moving relative to the container. So the fluid is stationary inside of the container. Even though the container is moving, the fluid is moving with the container, which means that there's no relative motion between the two, i.e. this is what we call a static fluid. So the first thing we're going to start looking at then are these static fluids. So fluids which are at rest relative to our container. So good. So the first thing we want to look at is this type of scenario. So let's say inside of here I have a straw. Here's my straw. And I have a fluid. Now what happens if I say block my thumb on the top and I pick up my fluid? Well, in this case, we can see the fluid is actually stationary. It's not falling down. Now, what can we say about that? Well, what we can say is what? The fluid, in this case water, which has water coloring in it, has a mass to it. And I know that because if I move my thumb, that's going to free fall and it's going to fall down. So in this case, again, if I block it and I hold it up, what I know is that it has a mass, so it has to be gravitationally falling. So again, if I move my finger, it free falls downward. But again, in this case, when I block my finger on top, what we can say then is what? It's not falling, which means that what? There must be a force on the bottom which is pushing up, causing this thing to be stationary. Okay. Now, what I also know is that currently I am in a fluid. Right? I am in air, which means that there is a pressure from the air, which means that the pressure on top here can't be the same as it is with the pressure on the bottom, because if this pressure was the same as this pressure, then the only force that would exist would be the downward force, which is going to cause this thing to accelerate downward at the rate of g, right? Gravitational force. So what that means then is that I have to have a pressure down here and a pressure up here, but those two pressures must be different. And more importantly, the pressure down here, where my thumb is moving, must be greater than the pressure up on top, because I have to have a net upward force. Okay? And again, pressure, if I have a pressure, that means I have a force perpendicular to the area. And again, if I move my finger, all that is simply going to fall down. So we want to know then is, how is the pressure down here different than the pressure up here? Okay. So to do that, let's draw exactly that scenario. So here, let's say that's what? We have a cylindrical column of fluid. So here's my cylindrical column of fluid. This thing has a mass to it, so there's going to be a center mass weight pulling down in this direction. So here there's going to be a pressure pointing upward from here, so this is going to be our pressure. Let's call that pressure P2. Up on top, there's also going to be a pressure. That pressure is going to be pushing downward, and let's call that pressure P1. Okay. Now, since there's a pressure P1, what we know then is there has to be a force per unit area pushing straight down, so we're going to call that F1. And then here, we also have to have a force pushing upward, and we're going to call that F2. Okay. Now, let's say this has a cross-sectional area A. Down here, this also has a cross-sectional area A. Let's just pretend that they're the same area just to make our lives a little bit easier. So,
intensity and everything you do is amplified in the playoffs, Howie.
Sorry about that. Okay, so good. So in this case, we can then say that this is a static situation. So we can then say that what? The sum of the forces in, say, the y direction are equal to 0. So let's choose positive y going upward. So this means that we have what? F2 minus F1 minus the weight of our system is simply equal to 0. And now let's solve this for F2. So this tells me F2 then is going to be equal to F1 plus the weight of our system. Okay. Now, we know F2, though, from pressure. So remember, pressure is equal to the force per unit area. So that means F2 is simply equal to the pressure 2 times the cross-sectional area. So it's going to be P2 times A. And that must be equal to, by the same logic, P1 times A plus then. Now, since we have mass, we can write that in terms of our new favorite friend, density. So it's going to be the density times the volume times G. Now, in this case, that means this has a density. Let's say this has a height of h. So in this case, we can write the volume then is simply the cross-sectional area times the height. So finally, this is going to become P2 times A then is equal to P1 times A plus rho times A times h times G. Now, since all these cross-sectional areas are the same, we can cancel those out. Whoops. There we go. So finally, we get then that P2 then is equal to P1 plus then rho times h times G. So this is what we call pressure versus depth. So what this says then is if I know the pressure at some point here, point 1, so let's call this point 1, I can then determine the pressure at another point P2 by simply knowing the density of the fluid versus the height of the fluid. So in this case, if I know that this is some height of say 1 meter, this is air, for example, so it has a density of 1.29 kilograms per meter cubed, then we can determine the pressure at a point lower than the pressure at the point higher. Right? Now, what does this say? So this means that if I was in the water, and again, let's say I'm near the surface of the water, but as I go down deeper and deeper in the water, what happens in that case is that the pressure becomes greater and greater and greater and greater, which is what we feel if we go very far down and say we're swimming. So again, what happens is if you go swimming deep enough, your ears again will start to hurt. They're going to start to pop. And again, that's because that now there's so much pressure, that water pushing on your eardrums, that it's actually going to try to compress them and push those in, which actually causes that pain. This is why if we go very far deep enough under the water, we actually need to wear things like scuba suits, which actually are trying to pressurize. So in that case, you have so much more pressure trying to push in that you need to pressurize with air to push outward to make sure that you stay at exactly the pressure that you want to be at, which is closer to atmospheric pressure. Otherwise, you're going to be squashed like a grape. Right? You're going to die. Conversely, this also says that if point 2 was actually up here, what that says then is that the pressure at 1 related to the pressure of 2, where 2 is actually higher, this now would become a negative sign, which means that the pressure above must be, again, less, right? So again, we already talked about this, but this is when you go up in an airplane. When you go up in an airplane, what happens then is that the pressure higher in the atmosphere is much less than the pressure lower in the atmosphere. So again, in that case, your body starts to expand, which then causes your ears again to pop. So again, this is called pressure versus depth. So this tells us how the pressure changes as we go down deeper and deeper into a fluid, or higher into a fluid as well. So this is what we call pressure versus depth. Good. Now, we can use this pressure versus depth to talk about our next topic, which is called Archimedes Principle. This is what we talked about in lab. Well, let's actually understand what we were talking about in this lab. So, Archimedes Principle. Now, Archimedes Principle, as we wrote down for the lab, I'm not going to write it down, but again, what it says is that any object which is partially or fully submerged in a fluid will feel an upward force which is equal in magnitude to the weight which is displaced of the fluid which is displaced. Okay, so again, what does that mean? So that means that if this was my object, okay, where this thing has volume of the object, and let's say for now this thing is fully submerged. So if this was fully submerged, again, now what we know is what? If this thing is simply sitting here, again, there's going to be a pressure downward from all of this fluid pushing in this direction, which means that there is a force pushing downward. So we're going to call that F1. Down here, again, we have all this fluid which is pushing upward, which means that what? This thing is going to feel an upward force F2, But again, since this is in a fluid, now we know pressure versus depth. We now know is that what? The force down here is greater than the force up here, which means this is going to result in a total upward force, which is what we call the buoyant force. Okay? So this is actually where this comes from. Now, the buoyant force, as we talked about in lab then, has a magnitude which is equal to the weight or the mass of the fluid times the acceleration due to gravity, which is being displaced. So again, this is going to be equal to the density of the fluid times the volume of the fluid times g. Now, again, as we talked about in the lab, in this case, what will happen then is what? If the object is fully submerged, if this thing is fully submerged, so if it's fully submerged in this case, then the volume of the fluid is exactly equal to the volume of the object. So in that case, it's simply going to be equal to this. Right? If it's partially submerged, so if it's partially submerged, in this case, the volume of the fluid will not be equal to the volume of the object, but it's going to be some fraction of it. So for example, if this was the line of the fluid, so all my fluid in this case existed here, in this case, then this total amount inside of here would actually be equal to the volume of the fluid. Okay? So in this case, the volume of the fluid then is going to be some fraction of the total volume of the object itself. So again, this is what we call Archimedes Principle or buoyant forces. So again, this just results from the fact that the pressure at a higher point is less than the pressure at a lower point in some sort of fluid. So in this case, this thing is being pushed upward due to the fact that these two forces are different, i.e. since this force down here is greater than this force up here. Now, again, this is the volume of the fluid which is displaced, not the volume of the entire fluid. So it wouldn't have anything to do with this fluid out here. It only has to do with the fluid which is being displaced. So in another video, we'll do a bunch of examples of this, but you've already basically seen this in lab. The last thing we're going to talk about for static fluids is what's known as Pascal's principle. So let's talk about Pascal's principle. So what does Pascal's principle say? So Pascal's principle says that if we have an incompressible fluid, i.e. a liquid, in some sort of closed container. So let's say here's my closed container. Put a couple different tubes on here. Let's put a small, so a medium-sized tube, a small tube, and a larger tube. And let's say for funsies, we have corks on these things. So here there's a cork, here there's a cork, and this one also has a cork. What Pascal's principle says is what? If I apply a force straight down here onto this cross-sectional area, where this one has a cross-sectional area of A, this one, say, has a cross-sectional area of A1, this one has a cross-sectional area of A2, then the pressure that I change in this system by applying this force downward, which basically means that when I push this downward, there was already a pressure, but now there's a new pressure, so i.e. there's a change in pressure. What happens then is, according to Pascal's principle, that this change in pressure generates a change in pressure at each one of these other corks, which results in an upward force on each one of these different corks. So this one then is going to experience a force F1 up in this direction. This one's going to experience a force F2 up in this direction. But what Pascal's principle goes on to further say is that what the change in pressure, which occurs at every single one of these corks, i.e. in every one of these tubes, is identically the same as the change in pressure which I apply here. Okay. So that means the resulting change in pressure here is the same as the resulting change in pressure here, which is the same as the resultant change in pressure here. So what this goes on to say then is that what? Since the change in pressure is equal to the change in pressure, that means that the force per unit area on the original tube, or the original cork at which I push down, then is equal to the force per unit area on each one of these individual tubes. So who cares? Well, what this means then is if I go ahead and solve this, this means that the force resulting on this tube, say here or here then, is going to be equal to the original force times the ratio then of the two areas. So, what does this mean? So what this means then is, for example, let's use this as a medium one and this is a small, and again this is a large. So let's say if I'm looking at this one. So if I apply a force onto a cross-sectional area which is smaller than the other cross-sectional area, what that means then is what? So here, if I apply a force onto this medium-sized cross-sectional area, so this is kind of small, but that force then it registers onto a larger cross-sectional area. What happens in this case then is that this becomes a large number, this becomes a small number, and if I take a large number, divide by a small number, that's an even larger number, which basically means that what? The force which is then generated here becomes much larger than the amount of force that I applied originally. Now, let's contrast it in this case. So here, I have a medium-sized area, I have a very small area, which means here, this is a small number divided by a large number, but a small number divided by a large number is an even smaller number, which means that what? The force, which is generated here, is actually much smaller than the original force at which I applied. So, ultimately, all this says then is what? By applying a force to an area, I can then use the change in pressure, i.e. the fact that this is an incompressible fluid, to then cause that to have a force here and here, but the size of those forces are now dependent on the ratio now of these areas. So again, if I apply a small force to a small area, I can then get a large force on a large area. But if I apply a force to a larger area, so let's say a large force to a large area, that then gives me a small force on a small area. So what are some of the uses of this? Well, first thing is a hydraulic, right? Like a hydraulic lift where you lift your car. So in that case, what you do is you apply a very small force to usually something very small, which then has a tube which then runs through it with an incompressible fluid, which then causes the hydraulic, which has a very large cross-section area, to apply a huge amount of force to be able to lift your car. So in that case, conceptually wise, it's a lot easier for me to put a small force onto a small area than it is to have a very large force and try to push something up like my car. So for example, it would be like me trying to bench press my car. Might be able to do it, but I'm not going to get it very far. Alternatively, again, I can apply a very large force to a small area and get a very small force and then on a very small area. Another place that this is very useful for are things like toothpaste, right? So what do you do with toothpaste? Well, you have a tube, you squeeze the bottom of the tube and the toothpaste comes out. Hydraulics, that's all it is. So it's Pascal's principle. I apply a force to one area, that then applies a force to a smaller area, which then causes the small amount of force to get the toothpaste out. Another example would be the Heimlich maneuver, right? So what happens in that case then is somebody gets something stuck in their throat. So you apply a force here, that force that you apply then generates a change in pressure. That change in pressure then applies a force to the piece of material, say food, stuck in a person's throat, which then causes it to actually shoot out. So all of these are examples of Pascal's principle. So again, Pascal's principle says that again, if I take a small force, apply it to a small cross-sectional area, I can then get a very large force onto a very large cross-sectional area to be able to do something like lift my car. So here's my car. This then generates on a force. Let's call this F1A1 and then F2A2. So in this case, I can use a very small force on a very small area to then generate a very large force onto a very large area. So again, practically speaking, it's a lot easier for me to apply a small force on a small area than it is to apply a very large force to move something. Now this sounds great. Now what is the drawback of this? Well, so let me rewrite this over here. So F1, say, is then equal to, actually let's call that F2. Do it Fi. So Fi then is equal to what? F times AI divided by K. So let's work with that. So let's think about the amount of work which is done. So here, if I apply this force in this direction, I have to move this thing then down a certain amount of distance, and let's call that simply the distance of d. Okay. Simultaneously, this one then is going to move up some distance of, let's call that di. Okay. So let's think about then the amount of work that I have to do. Okay. So let's start on this side. So the work that I do then is going to be equal to what? The force times the distance. Okay. Now, from here, this is then going to be the force then. Let's do it this way. So the force I do on one side and the distance I do on the other side then is going to be equal to the original force that I apply times an area AI divided by A times the distance DI. Now, what I also know though is what? Since this is an incompressible fluid, what has to be true then is the amount of volume here must be equal to the amount of volume here. So here, the volume simply is going to be what? A times D. The volume here then is going to be what? AI times DI. Those two volumes have to be the same. So here, this then tells me that DI times AI must be equal to D times A, which means DI then is going to be D times A divided by AI. Okay. We'll come back to that in a second. Now if I plug that in here, this then is going to be the same thing then as what? F times AI divided by A times D then times A divided by AI. But here we can see then is that this A cancels with this one, AI cancels with this one, which means that F then is going to be equal to simply, or the work then is equal to F times D. So what this means then is that what? The amount of work I do on the large is exactly equal to the amount of work that I do on the small. So again, here, if I apply a small force to a small cross-sectional area, I can then get a large force on a large cross-sectional area. However, the amount of work I do here is exactly the same as the amount of work here. Now, let's look at it further. So what this says then is, again, here I'm applying a what? On a small cross-sectional area to a large cross-sectional area. So here, this is going to be a small number divided by a large number, which is a very small number, which basically means that what? Here, I have to move this thing a certain distance, but the large force I'm applying on a large area, I can only move over a short distance. Okay. So ultimately what that tells me then is what? Here, to move my car a substantial distance, I have to move this one a much greater distance to get my car to move up. So for example, again, if I apply a small force here to a small cross-sectional area, but I only push it down, say, a foot, then on this side, I'm only going to be able to move it maybe a half an inch. So to move my car up enough so I can fit my big body underneath it so I can actually do some work on it, I'm going to have to move it on this side, say 10 feet, to move it on this side, say a foot. So again, the drawback here is what? Even though I'm getting a large force on a large cross-sectional area, I can only move it a very small distance compared to what I have to do over here. But this is done in such a way that the amount of work that I do over here is exactly the same as the amount of work over here. But again, if we think about it, it'd be like the same thing as me taking this piece of chalk and carrying this a mile versus me trying to bench press my car a half an inch. Practically speaking, it's a whole bunch easier for me to take this thing and simply carry it a mile as opposed to me trying to bench press my car and even move that thing a half an inch. So, even though, again, we can apply a small force to a small area and get a large force on a large area, the kind of drawback is we can only move it a very short distance. But, again, it's easy enough for me to apply a small force to a small area over a large distance as opposed to trying to apply a large force over a large or even over a short distance. So no matter how I want to look at it, the amount of work I have to do is identically the same. That doesn't change. I still have to do the same amount of work. But the benefit is that, again, it's much easier for me to apply a small force over a large distance as opposed to a large force over a very short distance, practically speaking. So the work is still the same, but again, I can only muster up so much force, and after that, I can't do much more. So good. So these are static fluid. So again, a static fluid is a fluid which is not moving relative to the container. So here we saw pressure versus depth. So again, if I know the pressure of this depth, I can now determine the pressure at any other depth, either below that or above that. We saw, again, buoyant forces, which we already saw in lab, but again, that's resulting from the fact that those two pressures are different, which applies two different forces. So the force down here will be less than the force up here, generating a total force upward. And then finally, we have Pascal's principle, which says, again, if we apply a force in a closed container with an incompressible fluid, then the change in pressure throughout is exactly the same, which will then allow us to have different forces. So in the next video, we'll do some examples of these, see how these things work in different calculational cases. And then after that, we'll look at what are known as dynamical fluids. So fluids which are actually moving, and these fluids are moving relative to the container. So these situations are things like your plumbing, right? How do we get water up into the house so we can actually take a shower and wash our hands and do all that beautiful stuff? Why we can fly planes, why we can sail ships, right? Why we can actually do all these things. So this is what we'll look at in a couple videos.